Okay, this is the Chapter 11 and Chapter 12 mixed homework from, it was due November 19th. So this first one wants the full mechanism and the products for this reaction. So this is going to be a normal electrophilic addition to an alkyne. I'm going to redraw this in a slightly different way. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And then my triple bond was here between carbons 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. Okay, this is where the triple bond is now going to be a double bond. And because this is symmetric, I can put this plus charge on either side, right? And that's the same thing. There's really only one carbocation, one unique carbocation that can be formed here. Then my bromide is going to come in and attack that position. I'm going to attack that carbocation, I should say. And now I'm going to have a bromo group here on this alkene. Okay, then remember, when we have excess HBr, as this problem said, we're going to continue on to brominate this alkene as well. Okay, and remember, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember that the carbocation is going to be more stable where that bromo group already is because of resonance, right? Because this bromo group has these lone pairs. I can make a double bond to give us an extra resonance stabilization for this carbocation. Okay. Then again, my bromide I generated from this step is going to still be hanging around to attack that carbon as well. Okay, so I end up putting two bromines on the same carbon and getting rid of taking my double bond all the way, or sorry, taking my triple bond all the way down to just an alkane now. Okay, next one. This one says, what is the alkyne starting material that would lead to this product? Okay, so while my alkyne is going to, if we're just doing this in one step, my alkyne definitely needs to have this benzene ring on it as well. And then remember, we can turn an alkyne into a ketone. If we have an internal alkyne, we can turn it into a ketone. And this carbon that the ketone is on must have been part of my triple bond. So I know this is one of my carbons that has a triple bond to another carbon. It can't have a triple bond to this side because then this carbon would have too many bonds. So it must be, triple bond must be between these two then. Okay, so it's between this first carbon off the ring and the second carbon off the ring. So 1, 2, and then there's one more carbon at the end. Okay, so that's the alkyne I must have started from. Now let's show the mechanism. Okay, let's show the mechanism for this. So the reagent that this pen I think is out of ink, the reagent that we use for this, we talked about in class, was triflic acid and water. Right? So the mechanism for this, we protonate our alkyne first, and we make our most stable carbocation that we can, which is going to be the one that's on benzylic, right? It's adjacent to the benzene ring. So carbocation here, and then that means my H went here. Right? And then we do this, the conditions we would do this reaction in would be, if I wanted to show this up here, would be triflic acid and water. Right? And this would be the actual reaction that we're looking at here. Alright, so this is where my water comes into play. Water is going to attack here on that carbocation. So this is not ink too. Okay, so here's where my water attacked, and now I have an OH2. Okay, and then another water will just come in and deprotonate this to give me my enol. And the fact that I just said enol should be setting off alarm bells in your head of what the next step should be. Because remember, we said enols don't tend to stay enols. They tend to tautomerize. Whether it's acid catalyzed or base catalyzed, they tend to turn into a C double bond O, because that's going to be more stable. Okay. In this case, we're under acidic conditions, so we want to show the acid-catalyzed tautomerization to form the enol. Okay. So you can just pick up an H plus from solution. You could show this as being an H plus that's attached to a triflate as well if you wanted to. Hang on one second. Let me pause. Okay, like I said, you could have showed this H coming off of a triflate if you wanted to, but we'll just say we picked up a proton from solution. Okay, and that's going to give me then a carbocation. Right, and my carbocation is going to be on that carbon with the oxygen attached, because this lone pair can then stabilize that carbocation, which cannot stabilize this carbocation on this side. Okay, and this is where the whole tautomerization comes from. This OH then is going to now make a double bond, C double bond O. Okay, and then this will finally just get deprotonated by another water molecule to give us our product. Okay, so kind of a long mechanism. The tautomerization part takes, several steps, but that's how we end up with a ketone. And you would expect to see, maybe a little bit of this ketone on this side as well. But because this cation is so much more stable, this is definitely going to be the major product. Okay, we might see a tiny bit of the other ketone in the other position, or the carbonyl carbon on the other carbon of the alkyne. Okay, remember we said whenever we have an internal alkyne, you have to be careful and watch out for mixtures. Okay, next one. Okay, next one is now into chapter 12. So this one says we're using this molecule, and then it said CH2N2, hang on, which one is this, 26? Yeah, CH2N2 and light. Just checking to see if it said light or heat. And remember, this really is just generating this carbene, okay, this methylene group. It's just carbon with two H's and a lone pair. So we know this is going to make this three-membered ring, the cyclopropane ring. Right, that's what carbenes do. That's the only reaction we know to do with carbenes. So we just need to make our three-membered ring. And remember, when you're doing these, that this carbene can attack from either face of the alkene. Okay, so I could have my carbene, that carbon now going back into the page if I want to keep this rectangle, or this square, this ring, cyclobutane ring, in the plane of the paper, which I would like to do. Okay, then I need to show this going back, right? Because I've already shown two in-plane bonds from this carbon. And then I'm also going to get the other enantiomer, which I'll go ahead and draw the other enantiomer too here. Okay, there are the three-membered ring. This should look a little bit more like a triangle than it does, but hopefully you get the idea. Okay, and this is going to be a racemic mixture. Okay, last one. This one asks us what reagents could we use, or I think maybe it says alkenes in particular. Show how each of these things can be produced from an alkene. Okay, so the key thing we want to kind of circle in on is this cyclopropane ring. We only really know one way to make these three-membered rings, and that's from alkenes. Okay, we said we're starting from alkenes in each of these products. So the first thing I would do is just redraw this chain without the cyclopropane ring, right? Just take that top carbon out, that apical carbon out of the structure, and this will be where your double bond is, at the kind of the base of the triangle. So I'm just going to redraw this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Oh, I screwed up my drawing, didn't I? I screwed up my drawing a little bit. Let me try this one again. Okay. Because I need to keep this. The other thing that's important is to consider the stereochemistry of your alkene. Since these are cis, I need to be starting from a cis alkene. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. So this is my alkene. Okay, for this one, same idea. Right? 1, 2, 3, 4, 5, 6, 7, 8 carbons again, but now this needs to be trans, so that's why I left this trans. Okay, so this would be where my double bond is. Then the alkene from this one. Okay, alkene here. Again, I said this is the new 3-membered ring. This must have been where my alkene was to start with. Okay, so now I just need to figure out what reagent do I use to make a carbene that then can add to each of these alkenes to give me the proper 3-membered ring over here. This one, right, I'm really just looking at what is this top carbon. This is just a carbon with 2 H's, so that must be the carbene that I need. But I need to remember what reagents I use to generate that carbene, because I can't just add this out of a bottle. I can't go to Sigma Aldrich online and buy this in a bottle. What I can buy is this, right, just like we talked about on the last problem, and use heat or light to generate that radical, or not that radical, excuse me, that carbene. Okay, same thing down here. I must be starting from just a carbon with 2 chlorines. How do I actually generate that carbene? I generate that from chloroform. Let's write that the correct way. CHCl3. Generate that from chloroform and sodium hydroxide. Really, this should be above the arrow. This is not a solvent. And then down here, similar thing. CHBr3 and sodium hydroxide is going to give me this carbon with just 2 bromines, right? This is how I generate my dihalocarbene, either dichlorocarbene or dibromocarbene. If I want to just generate this methylene or just this carbon with 2 H's, I use this reagent. Okay. Okay, last one, 35. It's just looking at this electrophilic addition to various alkenes, and it tells you that the rate increases the more substituted the alkene is. If you think about it, when we're doing this type of reaction where we're adding to some electrophile, right, the alkene is acting as the electron donor. The alkene is the electron rich. Okay, there's the electron rich, species in this generic kind of electrophilic addition reaction to an alkene. So the more electron rich that this alkene is, the better it is at making this type of bond, okay, doing this electrophilic addition. Okay, so the more donating groups that have, more substituted the alkene is, or the more donating, the more alkyl groups the alkene has attached to it. Okay, the more of these are R groups and the fewer of these are H's, then the faster the rate is going to be. Okay, that's the end of this one. Now we're fully into chapter 12.